In this tutorial, we're going to calculate a system's center of mass. So imagine that in 2 dimensions, we have a distribution of masses that looks something like this, where these could represent atoms in a molecule or stars in a star cluster. It doesn't matter, the strategy is the same. The goal of calculating the center of mass is that if we were to exert a net force on this system of 5 masses, the force would act as though it were operating on the center of mass. Similarly, if this system were accurately described by the equations of motion, then those equations would actually apply to the motion of the center of mass. So it makes sense to want to describe where the center of mass is relative to the 5 objects. The first step in doing this calculation is to establish the masses and positions of the individual objects. So let me put a spatial grid down, and we're going to assume that each of these boxes has a side length of 1 meter. So obviously we're not modeling molecules or star clusters, but that's okay. Whatever these masses are, we'll model those. We'll further assume that the red masses have a mass of 1 kilogram, the blue masses have a mass of 2 kilograms. And I'm going to go through and just arbitrarily number them for bookkeeping purposes. So now we just want to go through and list the masses and their position vectors for each of these things, bearing in mind that the origin is located at point 3. So M1, I said the red ones have a mass of 1 kilogram, and its position vector relative to point 3 is minus 7 meters I hat, minus 5 meters J hat. Similarly, for mass 2, its mass is 2 kilograms now, and that's its position vector. Mass 3 is located at the origin. It has a mass of 1 kilogram. Mass 4, there's its mass and position vector, and similarly for mass 5. Our goal is to apply this equation for the center of mass, and it's 1 divided by the total mass of all of the individual objects, multiplied by the sum of each individual mass times each individual position vector. Since we've compiled our listing of the masses and position vectors, I'm going to temporarily erase the figure on the right, and we'll get started. First step, easiest calculation you'll do all day, is just to calculate the total mass. So that ends up being 1 plus 2 plus 1 plus 1 plus 2 kilograms, which gives us a total of 7 kilograms. That's the total mass, and I'll write that over on the left. We'll need that later. Now let's go through and calculate each individual mass times its corresponding position vector. So for mass 1 times R1, that's just 1 kilogram times negative 7 meters I hat minus 5 meters J hat. If we multiply that through, that becomes M1R1 equal to negative 7 kilogram meters I hat minus 5 kilogram meters J hat. So it changes the units, but not any of the magnitudes. Okay, M2R2, same idea, except now we're multiplying by 2 kilograms, so we get minus 8 kilogram meters I hat plus 10 kilogram meters J hat, and it's going to be the same story for the other 3 masses. Here's M3R3, that's at the origin, so it's still 0, 0. M4R4, and M5R5. The only challenge in computing these numbers is making sure that you remember to multiply it by the mass, and that's particularly important when the mass is not 1 kilogram. So now let's apply the equation for the center of mass. And the first step will just be to divide by the total mass. So we'll calculate this term first, and that's just 1 divided by 7 kilograms. Okay, that's easy enough. Now we want to take the sum of the individual m times r's. The easiest way to do that is first to gray out the intermediate calculations here, because we just want the answers. And we're just going to go through and add up the I hat components first. So that'll be minus 7 plus minus 8, that gives us minus 15, plus 0 is still minus 15, plus 3 is minus 12, plus 12, hey, that's 0. So actually, the x component of the center of mass is going to be 0, and that'll be 0 kilogram times meters times I hat. What about the y component? Well, now we do the same thing in the other column, right? So we add together all these numbers. Minus 5 plus 10 is plus 5, plus 0 is still plus 5, minus 4 is plus 1, plus 4 is plus 5. Okay. Check my math if you don't believe me. That comes out to 5 kilogram meters times J hat. Last step is to go through and remember to divide by 7 kilograms so that we actually get a position vector out in meters. So we do that, and we find that RCM is 0 meters times I hat, plus 0.71 to 2 significant digits, meters J hat. So that describes the position of the center of mass. Graphically, what does that mean? Well, if we go back to our image here, where we actually put the masses back on screen, the center of mass we decided to define relative to point 3. We put the origin at point 3, so that means any position vectors that we're dealing with now are relative to point 3. Therefore, the center of mass is located at x equals 0 and y equals 0.71 meters, which is just slightly above 0.3 from this perspective. So that means that if we were to apply a net force to this system of 5 masses, it would act as though it were operating on that black dot I've just drawn. Likewise, if the equations of motion applied, it would be that black dot's motion that we were computing. All of the other masses would move relative to that.